And I trust that if I do not get this video on YouTube and posted, that Andrea will remind me tomorrow at the beginning that I need to remember to upload these videos. Okay, so let's talk about the magnetic field lines. First of all, magnetic field lines are not real. They don't really exist. They're just a visual tool for us to use for our imagination to be able to visualize something that is otherwise invisible. Like you can't see it. It's not obvious that there's anything there. But obviously we can do tests to reveal that there is a magnetic field. And the best test that you could put in there to just determine whether there's a magnetic field or not is to just use a compass. Right, and tomorrow I'm going to use one of the PhET simulations, and we're going to look at this magnetic field. And what I'm going to show you right now, you'll see it kind of displayed for you in another way tomorrow. But ultimately, the purpose of using all field lines, by the way, that's all field lines are imaginary. Like they don't really exist. They're just a tool for us to visualize something that is very hard to visualize. Now, the gravitational field lines and the electric field lines started on the object. So gravitational field lines start on the surface of the object, and the electric field starts on the surface of the charged particles. This field is totally different. It does not have a starting point. There is no starting point for it. It is a single continuous loop. That's totally different than the other field lines. They started at a point and they ended at a point. And magnetic field lines, they don't end. They never end. They just loop around and return back to the same starting point. So, that said, there is a kind of an orientation to the magnetic field lines. And can I ask you guys a question? Is it blurry? Are you guys able to see? Just let me know. Thumbs up
It's
if you see
clear.
it. It's clear? Okay. Because my screen, I don't know, it's weird. It's weird since I'm actually have both computers here that it kind of looks like it goes out of focus once in a while. So we are going to talk about something called the North and the South Pole. Okay. On the Earth, there is an actual North Pole where you could go and stand on it. It's almost like there's an imaginary pole going through the Earth, and that spot, the North Pole, represents where that pole would exit the surface of the Earth, and that is the axis on which the Earth is rotating. It has a definitive point. You can go to it and stand on it. The magnetic North Pole is not like that at all. Okay, the North Pole is essentially that end of the magnet. The entire end of the magnet is the North Pole. It's not just a specific spot. So there's a big difference between the geographic pole of a sphere and what we're talking about for magnetic pole. The magnetic pole is not a destination that you can arrive at and you are officially at the North Pole. It is a region of the permanent magnet where the magnetic field lines are exiting. They exit the North Pole and they enter the South Pole. Now, again, they're imaginary, right? These are not real. So this was just an arbitrary decision. Somebody had to make this arbitrary decision, and it was David Faraday. He's the one who made the decision. Oh, I'm sorry, Michael Faraday. I can't believe I said David Faraday. Michael Faraday. He made the decision. He's the inventor of all the field lines. I mean, he's the one who came up with this like really amazing idea that you could visually see what was happening and develop an understanding of it by drawing these imaginary lines that represented the direction of the magnetic force that would act on an object at that particular point in space. So the magnetic field lines are very different in the sense that they do not start and end at a particular point, but they do leave the magnet at the north end and they re-enter the magnet at the south end, because remember, they have to complete the loop. So if they exit the magnet, then that means somewhere they have to enter the magnet, because otherwise how could they come back and the loop closes itself off? And so you get a single magnetic loop. All right, second thing is that the field lines do not cross. That's the same for all fields. There's no difference between a magnetic field, an electric field, and a gravitational field with respect to that. The field lines do not cross. Now they will change and they will alter their direction to accommodate the other magnet or whatever magnetic field is coming into the same region of space. So you can have two magnetic fields at the same region in space, but they are going to merge together to be a single magnetic field. So that if you could imagine drawing the field lines would not cross each other. Okay, essentially that's it. That's all you really need to know. I do want to point out a little extra thing. It's not really a requirement. It's actually almost obvious that this has to be the case just based on what I've already told you. But I do want to emphasize this point. Okay, I'm going to draw a picture so you can kind of visualize this. So I'm going to draw a permanent magnet directly under this picture, so it's going to kind of go along with what we're talking about right here. Outside of the magnet, just look at what it says. So the field lines exit the north and enter the south. So that means that the magnetic field lines outside of the magnet go from north to south. So if you were standing on the north pole of the magnet and you started to follow one of those field lines as it exits the magnet, what you would find is that it curves and turns all the way around, follows a big loop, comes all the way around to the back of the magnet, and then enters in through the south. Now remember, a magnet is a physical object, so we can't just go inside of it. The magnetic field can go inside. It has no problem passing right through all the atoms. But physically, we cannot go inside of the magnet. All we see is the outside portion. So the magnetic field lines go from north to south, but inside they do the opposite. And that is definitely something you might see on an IB exam. So they show you a magnet, and then they ask you the two questions. What is the direction of the field inside the magnet? What's the direction outside the magnet? And it's going to be every combination of these, north to south and south to north. Um, and that is just by convention, because we said that the north pole is where the field lines are exiting. So then if you follow that field line, you'll arrive back at the other end at the south pole, and that's where you'll enter. And then if you're inside the magnet, you can start at the south pole and follow that field line, if you could somehow get inside the magnet, and follow that field line through the magnet all the way until it exits the north pole. So let's draw a picture of what this looks like. I'm going to make this magnet kind of short and stubby. It's not going to be super long, but it is going to be a relatively large picture. So I'm going to use most of the page here. And we'll put the north and the south here. Let me get some of the drawing done so that we can then later we'll go in and fill in some of the gaps. So first of all, the magnetic field leaves the north and it enters the south. Now here's a kind of interesting thing about magnets. That is, it's true for electric field. You know, if you get really close to a charged particle, you will feel the electric field. Believe me, like it will be extremely strong and you will definitely notice it. Same thing for the magnetic field. When you get really close to the magnet, you'll notice, like, of course, it's really strong when you get close. But part of the reason why the magnet is so strong when you get close is it depends on which part of the magnet you're looking at. Over here at the ends, where you have lots of field lines that are trying to exit, you can see that the field lines are very concentrated over here. Now all these field lines have to curl around and go to the other side. I think I drew too many, didn't I? Yep, I did. Normally, so let me let you guys draw that portion first. Usually, the way we would do this is I would have you map out the magnetic field lines. I drew that totally asymmetric. I don't know why I drew two up here. I don't know, it's kind of a mess. But you do want, for every line that you see on the right, there should be a line on the left. Because remember, each of those lines is a closed loop. So it has to return back to the same point. This is what we could see. All right, I can see this by placing a compass outside of the magnet, and I'll show you that tomorrow with the simulator. I can put the magnet outside of there, and it will show me the direction of the magnetic field because that compass is a magnet. The compass needle is a magnet, so it feels magnetic fields, and all magnetic fields all magnets, I should say, want to line themselves up with the magnetic field. So if I were to put a little compass right here, it would point like this. And if I put the compass over here, it'll point like this. When I put the compass over on this direction, it's going to point like this. And as I move the compass around, you'll see the direction of that compass change as it reflects the direction, the changing direction of the magnetic field. But what we cannot see, and there's no way I could demonstrate it for you because I cannot physically get inside, if I cut a hole in the magnet, it's still, the hole is outside of the magnet. I hope that makes sense to you guys. I'm going to show you what I'm talking about in just a minute. But we know what the magnetic field lines do look like. So what needs to happen is these guys all need to be connected. And one thing you can see about the magnetic field lines inside of the magnet is just how concentrated they are. Look how concentrated. Every field line that went through the outside must pass through the inside, so it should be pretty clear that the inside of that magnet must be incredibly strong. I mean, that must have an incredible amount of magnetic strength when you have every field line that exists outside of the magnet exist inside the magnet, except they're compressed down to a space that's probably a centimeter or less. You know, the magnets are typically not super large. So when you, and I'll show you this tomorrow when we look at the simulator, you'll see that, again, I can't show you the inside. Okay, I cannot get inside of a permanent magnet because there's no way for me to physically do that. But you'll see when I bring the magnetic sensor down over here, is, oh, the field's not that strong. There's a little bit of a field, but it's not super strong. But as I pull it in from here, all the way up to the edge of the magnet, you might see it go from like 1 to 2 to 5 to 10 to 100 to 600 as I hit right here. The magnetic field strength gets super strong as we get very, very close to this guy, and that is because the field lines are all very, very tightly spaced together right here, and immediately after exiting the magnet, they start to spread out. And by spreading out, they weaken the magnetic force. But here, close to the end of the magnet, everybody's being forced to stay together. Everybody's still very tightly packed together. And that very dense number of lines tells you that the field would be very strong. It not only tells you the direction from north to south outside the magnet, from south to north inside the magnet. This is directly off the IB exams, why I'm showing you this. So you do need to know what's going on with the inside of the magnet. It's not enough to know what's going on the outside. And frankly, if you understand how magnetic field lines work, it's obvious. It's obvious that the field lines have to go north to south on the outside. Then on the inside, they'd have to go south to north. If I could, for just a second, I just want you guys to imagine what would happen if we broke this magnet in half. Well, what would happen to that magnet? Would we have like the South Pole? Would we have like cracked off the South Pole? The answer to that is no. That is not what would have happened. Okay, so there's that same magnet. I've now cracked the thing in half. Remember that the field lines are going like this on the inside. Okay, so nothing has changed on the inside of the magnet. The magnet is still a magnet. But look at what's happening. What's going to happen right here? The field lines are going to exit. And while they would like to try to go away from each other, what they're looking for, the field lines that lead the north end of a magnet are looking for a south end of a magnet to enter. So if it's closer to enter the south end of another magnet, they'll do that rather than curling around to themselves. So let me just show you what that's going to look like. So what happens when you break the magnet in half? You end up with two magnets, and each one has its own north and its own south. So when you break that magnet in half, you've created a new north and south pole. You've created a new place where the field lines will exit, and you've created a new place where the field lines can enter. So you can imagine that if we tried to cut a hole in the magnet to see what was going on inside of it, we still wouldn't see the right picture, because what would happen is the field lines would exit the magnet, travel through the air, and then re-enter in what would be effectively a new south pole on the other side of the hole. So cutting it in half, drilling a hole, it's not going to let us see what's going on inside the compass or inside the magnet, because outside the magnet, it's always going to be north to south no matter what you do. No matter how you try to manipulate that magnet, it's not going to show you what's going on inside. We know what's going on inside mostly because of our study of electromagnets. The magnetic field here is the same as what's caused in an electromagnet, and we know exactly how it works. On the electromagnet, the difference is I can get inside of it, because an electromagnet is just a coil of wires, and I can get inside the coil. So I can actually get inside physically. I can take my body inside and measure the magnetic field strength directly from the inside of an electromagnet, but I cannot do that with a permanent magnet. Okay, so that is all I wanted to go over for today. Tomorrow we'll go over, we won't finish the chapter, but we'll be pretty close. I mean, we've talked about a lot of different things. We talked about the right-hand rule. We talked about why is it that a wire